Hey everyone, this is lesson 831 on area ratios of similar figures. Okay, so up to this point, we've talked about finding the area of different shapes. Um, Oftentimes, we come across a shape that just is a lot of work to calculate the area of. So like the last lesson, we talked about finding the area of polygons. Um, if we're talking about shapes like a rectangle or a triangle, it might be fairly easy. But when we start talking about a hexagon or a pentagon, and then maybe if it's not even a regular polygon, we might not want to go through all the work to calculate the area. So if we could find an easier way, then that would be very helpful for us. And so that's what we're going to look at today, is really trying to find the area of complicated shapes without having to do so much of the work. And so let's start with reviewing and introducing what we're talking about today. So we've already talked about similar figures before. So we've kind of had a problem like this before where I would give you two shapes and ask you to solve for maybe the missing side. Now, given that these two shapes are similar, then we could use proportions to figure out the missing side length. You might be able to even look at this and maybe even guess what x might equal to in this picture. So I'll just ask you this: what's x equal to? Can you tell me? All right, if you said 6, you'd be correct. All right, so how did we get that? All right, so and how much are the sides growing by? All right, so if I look at the left side, which I have a measurement of 2, and the left side of the larger shape, I notice it goes from 2 to 4, which you might notice is twice as big. So you could make the assumption that if you're going from 3 to whatever this measurement is, it should also be twice as big. Right? So in this case, that would make this measurement a 6. So I'm going to put equals to 6. All right, so how much are the sides growing by? So we just said this 2 turned into a 4 by being twice as big. And the 3 and the 6, it looks like it got twice as big, right? So how much are the sides growing by? We would say they're growing by 2, right? Or yeah, let's just say they're growing by 2. And so what I want to look at is what's the linear ratio? So this is a reminder of some terminology we've had before. So the term linear is really just another word for sides. Ratio is another word for fractions. So when they ask you for a linear ratio or maybe even a linear scale, typically it's really talking about a fraction. So if I wanted to create the linear ratio from this enlargement from the small to the big, then I would say, okay, let me take the side measurements. Let's take the 4, which is the bigger side. That's where we end up with. And we're going to make a fraction by putting the 2 underneath it. So this 4 is the 4 on top, and this 2 is a 2 on the bottom. All right, so here's our linear ratio. All right, so linear ratio, does this reduce? Yes, it does. So we could also reduce this fraction, and we could reduce it to 2 over 1. All right, so here we could say is our linear ratio. Sometimes we might just say, oh, a linear scale factor of 2, because technically 2 divided by 1 is 2. But I want us to keep it as a fraction just so what we do a little bit later might make more sense, because these ratios aren't always nice whole numbers, right? So I don't want you to assume it's always like that. All right, so let's look at this. It's really the same picture, I just copied it over. But new question, what about the areas? All right, so let's see if we could kind of do the same thing, except look at the area ratio. So we already know the sides got doubled, right? So we already know these sides are twice as long. So if I ask you, well, how much bigger is the area? Most common answer is people are going to say, well, it's twice as big, right? So probably even some of you are thinking that right now. So if I ask you how much bigger is this larger one, you might say, oh, it's double. Well, let's look at the areas and see if that's true. So this is drawn to scale. So if you could either calculate the area, or we could just count the number of boxes in the grid. But for the most part, let's just do some calculations here. So area, in this case, this is a rectangle. So area of a rectangle is base times height. So I'm going to put 3 times 2, which then gives us an area of 6 units squared. All right, and then the second one, I've labeled it as them separately A1 and A2, so we could tell the areas apart. And so the second one, we would do 6 times 4. And so this would give us an area of 24 units squared. All right, now, just by looking at the areas alone, does it look like the area got twice as big, right? We went from a 6 to a 24. Is that double? All right, if you're still not sure, well, let's write an area ratio. Now, in the previous part, we wrote a linear ratio, which was focused on the sides, making a fraction of the sides. Here, when we talk about area ratio, it's saying basically, let's write a fraction ratio using the areas. All right, so let's put, so I'm going to put 24 over 6. That's all I'm doing, 24 over 6. So that's the 24 was the second one, and the 6 goes on the bottom. That was the original one. All right, so what is the area ratio? Well, 24 over 6, if it reduces, we want to try to reduce it. In this case, I believe it does. All right, so this reduces to, I believe this is 4 over 1. All right, so with the linear ratio, it was 2 over 1, and it was twice as big. The area ratio is 4 over 1, and how many times bigger was the area, right? So you'll notice this is 4 times as big. So even though the sides were 2 times as big, the area was 4 times as big. All right, so this is kind of our first example, but this is what we have so far. I want to try to summarize a little bit at a time. So how are the linear ratio and area ratio related? So we started with the linear ratio of 4 over 2, which simplified and reduced to 2 over 1. And we started with an area ratio of 24 over 6, which reduced to 4 over 1. So we're really looking at the 2 over 1 and the 4 over 1. And I want to see how these two numbers are related. So we know that the sides are growing by a factor of 2, right? The sides were twice as big. And the area is growing by a factor of, you tell me. All right, if you said 4, you were correct. All right, so sides are doubling in size, but the area is actually getting 4 times as big. All right, so is that always the case? And why is that happening? Does it happen for every single shape? All right, well, let's look at another example. All right, so here's a similar problem. I've just changed the size of the rectangle. I'm trying to stay with simpler shapes for right now. So I've given us more information, but now that you've already been prepped, let's look at creating a linear ratio and an area ratio. So we could look closely at how they are related to each other. So let's see, what is the linear ratio? Now let's look for, I want to have a reduced, you're going to have a fraction, and I want you to reduce it as much as possible. Again, you shouldn't be using a calculator, you shouldn't have a decimal, it should look like a fraction. So what is the linear ratio? All right, so if you said 3 over 2, you would be correct. And then second question is, what is the area ratio? And try to reduce that if you can. All right, so this would be, you would probably start with 18 over 8. The areas were given. And this does reduce, I think I could cut probably both of these in half. This would be 9 and 4. All right, so we have a linear ratio and we have an area ratio. All right, so how are they related, right? Is there any way I could have determined what the area ratio was without knowing the areas? So is that possible? All right, so let's look. All right, so this is what we have so far. So we had the linear ratio of 2 over 1, and we had its area ratio was 4 over 1. We just determined on this new shape, the linear ratio was 3 over 2, and the second, or the area ratio was 9 over 4. So like I said, without knowing the areas, can we have determined the area ratio just using the linear ratio, right? So what can I do to this linear ratio so that it turns into this area ratio? So if I have 2 over 1, what can I do to 2 over 1 to turn it into 4 over 1? And can I do the same thing for 3 over 2 to turn into 9 over 4? All right, so that's what we're trying to figure out, is what's the connection here. All right, so I'm not going to hold you in suspense much longer. I'm just going to tell you that this 4 over 1 is really the same as 2 over 1, which is the linear ratio, squared. All right, so 2 over 1 times 2 over 1, right? 2 over 1 times 2 over 1 is equal to 4 over 1. And so does that work for the second one? Does that work for these? So if I take 3 over 2 and I square it, right? So 3 over 2 times 3 over 2, because that's what squaring means, to multiply by itself. We're left with 3 times 3 on top is 9, and 2 times 2 on the bottom is 4. So that's exactly what we had over here, 9 over 4. All right, which means we could totally figure out what the area ratio just by using the linear ratio. So that's nice because that means we wouldn't have to calculate any areas in order to figure out what the area ratio is. All right, so for example, if I give you a linear ratio of 5/2, then the area ratio is, let's see if you could get this correct. It's going to be one fraction and then hopefully reduced. All right. All right, so if you got this correct, you should have thought of 5/2. We're looking at 5/2, and we're going to square it. So we want to know what that is. So 5 times 5 gives us 25, and 2 times 2 gives us 4. All right, so that's your area ratio. So if the sides are growing by 5/2, that means the area is growing by 25/4. Right? And those are actual numbers. If you want to turn them into decimals, you can after the fact, but it's a lot easier to work out once they're in fractions. Okay, so how does this help? Why do we even want to know an area ratio? So we figured out the area ratio without even knowing any areas. Well, how does that help? Well, now we have a way to find the area of shapes without doing complicated work. All right, so, and more so with shapes that are not common shapes. All right, so I'm not even going to get into like pentagons or weird triangle with quadrilateral shapes. There's other shapes that we could probably figure out with some work. This is a type of shape that there really is no formula for. Right? It's close to impossible for us to find this, right? So how would we even find the area of a shape like this? And so if we wanted to know the area of the shape, we would need to look at another shape that's very similar. And so in this problem, it mentions Kelly has this shape, and we know the area of the shape. So we already know the area of Kelly's shape, which is nice. And the only other piece of information they're telling us is this bigger shape is 5 times bigger. It's 5 times bigger. Based on that information, we know enough to find the area of this other shape, which otherwise we really wouldn't have any method to solve for this. All right, so once we know the area ratio, then we could use proportions, which is another method that we are already familiar with to solve. All right, so first question then is for you, what is the linear ratio? See if you could get this correct. All right, if you said 5/1, then you would be correct. Or if you said 5, that's fine as well. But 5/1, I like to leave it as a fraction because switching it to area ratio, now that you know the linear ratio, what is the area ratio? All right, so let's see if you got this correct. So our strategy for finding area ratio was to take our linear ratio and square it. So let me just rewrite that below. So I'm going to even write it out. 5/1 squared is the area ratio, which equals to 25/1. Because 1 times 1 is still 1, so that denominator didn't change. All right, so how does this help? Well, now we could set up a proportion. So we're going to take that 25/1, and now we know what the area ratios should be. So this is going to be 25/1. All right, what we plan on doing is figuring out what the actual area is. So the area that was given to us was 17 millimeters squared. That was given to us. All right, so does that go, that's going to go here. Does it go on top or does it go on bottom? All right, well, think about it. This is the smaller shape and we're going to a bigger shape. And so look at this fraction. Which number is smaller, 25 or 1? It's the 1 is on the bottom, so that means my 17 is going to go on the bottom. All right, which means the missing piece, which we could call x, that goes on top. All right, so that represents the bigger area. So this is our area ratio. Big area over small area. Big area over small area. All right, now all we have to do is calculate this. So if we actually multiply that out, you should end up with x equals to 17 times 25. And that is something we could type into a calculator if you don't know how to do that one. So 17 times 25 gives us, let me write it over here. So x equals to 425. This is area, so we're going to do millimeters squared. All right, so let's, all right, so we figured out the area of that odd looking shape, and it really wasn't too difficult, right? I know it's a little bit longer because I'm explaining it, but really just think about it. All we needed to know was how many times bigger was it? 5 over 1. We turned that to a 25 over 1. And then we were able to set up our proportion. 25 over 1 and missing area over given area. All right, and then cross multiplying those gives us our answer. Right? So this is kind of a general idea of what you need to be able to do. Next lesson, we're going to practice some more of this. So hopefully the more we practice, it'll make a lot more sense. This was more of an introduction to what we're going to be doing on the next lesson. All right, that's it for now. See you next time.